The ideal gas law looks at a gas under a particular set of conditions. So instead of having an initial pressure and volume and then changing the volume and seeing what that does to the pressure, it's just like a snapshot of a gas at a certain time. The formula for the ideal gas law is PV equals nRT. P being pressure, V is volume, N amount in moles, and R is something called the ideal gas constant, and then T is temperature. So the ideal gas constant is a constant value. It is right here. It is 0.0821. This entire thing right here is the unit of R. So you know how the unit of pressure can be like kPa. The unit of volume can be liters or milliliters. The unit of R is that entire thing, liters times atmospheres over moles times Kelvin. And because that's the unit of R, that determines the unit of the pressure and the volume and the temperature in the equation. So pressure in the ideal gas law always has to be in atmospheres, volume always has to be in liters, N is still moles, and temperature is still Kelvin, but it has to be those units in order to cancel with the units in R. So we're going to calculate the volume occupied by 0.845 mole, that's an N, of nitrogen gas at a pressure of 1.37 and a temperature of 315. So I know I'm using the ideal gas law here. Calculate the volume. Because I only have one volume, one pressure, I don't have two. So the only formula that I have that has one of everything is the ideal gas law, PV equals nRT. So my P is 1.37 atmospheres. My volume is my unknown. My moles is 0.845. R is the ideal gas constant. So it's a constant, it's always 0.0821 liters times atmospheres over moles times Kelvin. And then temperature is 315 Kelvin. Rearranging to solve for V, we get V is nRT over P. So 0.845 mole times 0.0821 liters atmospheres over mole Kelvin times 315 Kelvin over my pressure of 1.37 atmospheres. So I get a volume of 15.95. For significant figures, I have to have 3, so we have to round it to 16.0. With respect to the unit of that volume, moles here will cancel, temperature cancels, atmospheres cancels, and I'm left with a unit of liters. In this problem, I'm given 1.33 grams of helium, that's an amount. I'm given a volume, I'm given a temperature, and I'm determining the pressure. So again, just one of everything that tells me I'm using the ideal gas law. This one, however, is going to require quite a bit of converting because you do need those specific units. So my pressure is unknown. My volume is 648 milliliters. Volume has to be in liters, so we convert that to liters. N is moles. The amount has to be in moles. So again, we'll have to convert 1.33 grams of helium. Helium has a molar mass of 4 grams per mole. R is the ideal gas constant, so 0.0821 liters atmosphere mole Kelvin. And then T is 32 degrees Celsius, but you can't use degrees Celsius in ideal gas law or in any gas laws, so it's 305 Kelvin. Rearranging my formula to solve for P, I get nRT over V. So 0.03325 mole times my ideal gas constant, 0.0821 liters atmospheres mole Kelvin, times my temperature, 305 Kelvin, over my volume of 0.648 liters. So my pressure is 1.28487. Again, looking at units and how units are canceling here, I'm left with unit of atmospheres. This is asking for a pressure in millimeters of mercury, so I will just convert 1 atmosphere, 760 millimeters of mercury. I get 976.502, 3 sig figs, so 977 millimeters of mercury. The ideal gas law can be used to calculate molar volume and molar mass. We're going to just look at molar volume right now. So at STP, the mole or the volume of 1 mole of a gas is a constant value. STP stands for standard temperature and pressure. Standard temperature is 0 degrees Celsius and standard pressure is 1 atmosphere. So standard temperature and pressure, STP, is an actual temperature and pressure. So we're going to calculate the volume of 1 mole, so that's my N, of a gas at STP. And again, so that is a T, it is a temperature, it is a pressure. So I can use my ideal gas law, where my pressure is standard pressure, 1 atmosphere. My volume is my unknown. It has to calculate for 1 mole. R is ideal gas constant still. And then T, standard temperature, 0 degrees Celsius, which is 273 Kelvin. So volume is nRT over P, 10821, 273 over 1 atmosphere, and we get that volume is 22.4 liters. So that is the molar volume of a gas. The identity of the gas does not matter. 1 mole of any gas at STP, only at STP, 1 mole of any gas will occupy 22.4 liters. So that is a conversion factor. That's kind of our third and final conversion factor. We had 1 mole is the mass off the periodic table. We had 1 mole is 6.02 times 10 to the 23rd particles. And now we have 1 mole is 22.4 liters. So what is the volume in liters of 1.5 moles of nitrogen at STP? So again, STP is a temperature and a pressure. So I do have an N, I have a T, I have a P. It's asking for a volume. I could use the ideal gas law. But since we do have the molar volume of a gas, I could also just do a conversion. 1.5 moles, moles on the bottom, liters on the top. 1 mole at STP always has a volume of 22.4 liters. So you can do it either way, you will get the same answer. This next question, because it doesn't specify that it's at STP, I'm going to skip it, because if it's not at STP, you actually can't do it. What is the volume of 24.8 grams of oxygen at STP? So again, if you just forget about conversion factors, you could use the ideal gas law to solve this. But since I know about conversion factors and it's easier, I'm going to use that. So 24.8 grams oxygen. Oxygen is diatomic, of course, so 32 grams per mole. And then 1 mole, 22.4 liters. That's going to give me 17.4 liters of oxygen. Lastly, I have 4.5 liters of hydrogen. I don't know how many molecules of hydrogen I get. So 4.5 liters. Cancel the unit of liters, go to moles. 1 mole is 22.4 liters. 1 mole is 6.02 times 10 to the 23rd molecules. So that's going to give me 1.2 times 10 to the 23rd molecules. So you just use the 22.1 mole is 22.4 the same way we used any of the other conversion factors. Lastly, we have a little conceptual question here. Assuming ideal behavior, which of these gas samples has the greatest volume at STP? So if you think about your variables, you know that volume is related to temperature, it's related to pressure, and it's related to amount. Well, what I'm given is grams. I'm given an amount. But that amount has to be in moles. 1 gram of hydrogen is not the same amount of stuff as 1 gram of oxygen. So just without actually doing the conversion, hydrogen's about 2 grams per mole, oxygen's about 32 grams per mole. Argon's about 40 grams per mole. So I have the most hydrogen because I have about half a mole of hydrogen. I have 1/32 of a mole of oxygen. I have 1/40 of a mole of argon. So the most amount of stuff is hydrogen. And since hydrogen has the most stuff, the most amount, hydrogen also has the highest volume because they are directly related.